A continuous function over a finite closed region in its domain must take on both an absolute minimum and an absolute maximum value. We can search for these absolute extreme values by looking at any of the interior points of the region. We're limiting ourselves to where there are critical points, and then we can look over the boundary elements and do some calculus from Calc 1. If I think about this equation, z equals x squared minus xy plus y squared plus 1, only over the line y equals x in the domain, well, if I take that line in the domain, I can imagine intersecting the surface and I would get a curve. And then that curve might have a min or a max, so I need to find those locations. After we have a list of all the interior points and a list of any place on a boundary element where we might have a min and max, we simply look for the largest thing and the smallest thing. Those tell us our absolute min and max over the finite closed interval. So in this example, we're given z equals x squared minus xy plus y squared plus 1, and we're asked to find the absolute extreme values over the closed triangle in the first quadrant bounded by y equals x, which I've already graphed, y equals 4, and x equals 0, the y-axis. So here's my finite closed region, and I can imagine that this surface is some surface above it. So let's look for critical points in the domain. So I need a first partial and a second partial. Taking a partial with respect to x, I'll get 2x minus y. A first partial with respect to y, and I'll get minus x plus 2y. I need to look for places where these are simultaneously 0. So I get a system of linear equations in two variables, and I'll need to solve. And I have choices for how to solve it. I could get one of the variables by itself and use the substitution method. I think I'm going to multiply this equation by 2 and then use the addition method. So 2x minus y equals 0, and the first equation won't change. Minus 2x plus 2y is equal to 0. I add those together, and I'm simply going to get y is equal to 0. Now I need to look for the x-coordinate that corresponds to this, so I could plug them in, and I'm going to find that, well, x is equal to 0. And so the only critical point I have to worry about is the origin. Well, the critical points I'm supposed to list were supposed to be on the interior of my region. That's on the boundary. So it wouldn't make my list because it's not on the interior, but it's going to make my list eventually. And we'll talk about that in a moment. Because now what I have to do is search for where minimums or maximums could lie over the boundary elements. So I have 3 boundary elements to consider. X is equal to 0, y is equal to 4, and then finally y is equal to x. My original function, z is equal to x squared minus xy plus y squared plus 1. Well, if I'm only considering the path x equal 0, the y-axis, that means z would be equal to y squared plus 1. So what I'm really saying is over the y-axis, I would see the parabola y squared, z equals y squared plus 1, right? So kind of going up like this over that region, right? I could imagine there's a piece of paper here and I graph a parabola on it. So I get that part of y squared plus 1, starting at 0 and ending at 4. And this is really just doing some first calculus. I'm looking for where I might have mins or maxes of this function. So trapped in that plane, I could just imagine doing the Calc 1. And the only critical point for z equals y squared plus 1, thinking of z only as a function on y, would be where y is equal to 0. The extreme value theorem says that the only places I could have a min or a max for that 2D curve I graphed is at a critical point, 0, or at one of the endpoints. So, well, that's y equals 0 and y equals 4 are my endpoints. So, x is 0 everywhere in the little slice I'm talking about. I have to care about where y is 0 too because it's an endpoint. X is 0, and I have to care about that endpoint where y is 4. Well, that means the origin is on my list because it's the endpoint of that little strip of the y-axis, right? It's that finite closed interval from the extreme value theorem. And I have to consider that point too for the same reason. So I have a sneaking suspicion that I'm going to need to consider all of the corners of my triangle, right, because they correspond to endpoints of intervals. And then I'll have to care about any critical points over those boundary regions, reducing the problem down to that Calc 1 problem. The only critical point for this region was at one of the endpoints, so I don't have to worry about it, because the critical point's really on the interior. All right, so y is equal to 4. Z is equal to x squared minus 4x plus 16 plus 1 is plus 17. So now I have a function defined as, I have z defined as a function on x, and so that's some parabola over this line in the domain. And it's a parabola that faces upwards, so maybe there is a critical point in the middle I need to worry about. So let's take a derivative. And again, now I'm just trapped in that plane. These are really partials, right? Because y is equal to 4, but I really am just thinking of a Calc 1 problem here. Set that equal to 0. The only critical point I have to worry about is where x equals 2. Because this is a parabola, I know it's a min, but I could actually think of the first derivative test from Calc 1, where I put that 2 on a number line, and I ask myself, well, is the derivative of positive or negative over here? Well, if I plug in a value over here, I get like a 1, I get 2 minus 4 is a minus 2. If I plug in a 3, I get a positive, so definitely a min happening there, but I really just needed that critical point. So 2, because it's a critical point there, and y was 4. So that's a point that's on my list, which would be this point right here. Because this endpoint, the intersection of y equals x and y equals 4, that's the point for 4. All right, I have one more boundary element to inspect. But so far, I have 1, 2, 3 things on my list, including that endpoint at 4, 4 now, 4 things on my list. 0, 0 is an endpoint. 0, 4 is an endpoint. I have a critical point at 2, 4, and then the other endpoint here, 4, 4. At y equals x, let's see, z is equal to x squared minus x squared plus x squared plus 1. And z is x squared plus 1. So over that slanted line, I'd get another x squared, I'd get another parabolic graph that looks like an x squared plus 1. The derivative with respect to x is 2x. The only place that is equal to 0 is when x is equal to 0. So on this piece, I only need to worry about the 2 endpoints, which I'm going to write down as 0, 0 and 4, 4, but I already have those on my list because I've already written down all the corners of that triangular region. I have 1, 2, 3, 4 points to consider for the locations of my absolute min and absolute max. So I'm going to write down some x comma y's, and I'm going to find the corresponding z's. So I'm just going to go around. I have the origin, 0, 4, 2, 4, and 4, 4. The 3 corners of my triangle and the 1 critical point over a boundary element that I found. The only other possibility I could have had was some place where my partials were equal to 0 on the inside. And this example just doesn't have that. All right, so now I need to plug those ordered pairs into my original function to evaluate the z's. Well, plugging in the origin is very easy. I get out 1. Plugging in 0, 4, I would get 17. Plugging in 2, 4, let's see, that would be a 4 minus 8 plus 16 plus 1. So 17 minus 4 is 13. And then finally, plugging in 4, 4. 16 minus 16 plus 16 plus 1. 17. I found my absolute max and my absolute min. The absolute max of 17 occurs at the points 0, 4 and 4, 4. The absolute minimum value of 1 occurs at the point 0, 0. All right, we found the absolute min, the absolute max, and there's even a GeoGebra graph in the YouTube description and on our Moodle course page so that you can make sure that we actually worked it out correctly.